So thank you very much, Carlos, for the nice introductions. I am very excited to be here, and thanks for the invitation to speak with so many people. I hope it's okay because it's really a big pressure. But I am very happy to talk about. We are going above the surface of the sea, and I am very happy to talk about climate change and variability and atmospheric extremes in the Antarctic Peninsula. I will provide a kind of a review of what is going on in the last 8 to 10 years in atmospheric science in the region, which is more or less the time that I've been working on this topic. So I am very happy to talk about this, especially now that I am switching a little bit with more continental studies. But before starting to talk about this topic, it's important to frame a little bit the scales we are going to talk about because atmospheric science it's very important the scales we are talking about. So the geographic scale is very clear, it's Antarctic Peninsula, but more less clear is maybe the temporal scale, since as you can see here, many different atmospheric patterns works in different horizontal scales and also therefore time scales. Since we are going to talk more on the long scales, like in climate change and interannual variability, we are choosing annual stational scales, but I am also going to speak a little bit to more short scales as extreme events. Finally, also it's important to frame in terms of variable. I am going to focus more on temperature and wind and precipitation in this region. So, okay, let's start by looking the large-scale temperature trends in the Antarctic Peninsula. This plot from Jones and others shows the temperature trend between 1957 and 2016. It can be seen clearly two regions in Antarctica. One region where has not been almost any temperature trend, and this region of West Antarctica and Antarctic Peninsula that has been a very big temperature increase in the last 70 years or 80 years. And it's indeed a hot spot of temperature change, not only in Antarctica, but also in the world. So with that, it could be, okay, it looks very easy, but it's not that much. If we look closer to the changes, the picture is more complicated. For example, here I plot the mean daily temperature of the Antarctic Peninsula in this region here from area 5. And if I show this, you will see that we cannot extract from the daily temperature too much information, right? This is an example of how important it is to frame very well or scales. But this change, if we plot the mean monthly temperature, we start to see more interesting information. For example, we can see that while summer's temperatures have not changed almost, low winter temperatures have increased significantly. Indeed, if we average by years at this long scale for daily temperatures, also we cannot see too much, but if we make a zoom in the annual temperatures, we can see that has been a slight increase in the temperature since 1979. However, still this picture is very complicated. The increase first is not that evident, and if we take the first 2 decades of the 20th century, you can see a significant decrease in temperature. This is quite famous decrease that was identified first by Turner and others, which also showed that was caused by natural variability due to the lower than average atmospheric pressure over the Drake Passage. Following this study, it appears also one of Carrasco and others that show that this trend has already reversed and now we are already in a positive phase following the previous temperature increase of the 80s and early 90s. However, picking the years of the start and end of the trends, it's a kind of cheating. Uh, in a good way. Like we do it to show the biggest effects, but what happens if we had 1 year or more or less at the starting? For example, look this point, this beginning point. If we wouldn't have this beginning point, we would start in this year, and then this linear trend would be much more pronounced. This we can illustrate it by choosing randomly different starting and endings in the time series. Here I just made a program that choose randomly uh, time series of more than 15 years or 20 years, I cannot remember, and choose randomly the beginning and the ending year. And you can see that you can find either a big decrease or bigger increase. So the linear trends are very dependent on this, on the peaking years that we have. And this is why we try to illustrate in this article in 2018 that maybe it's not that famous as the paper of Turner and others, but we tried to understand how robust was this cooling trend that occurred at the beginning of the 20th century. This plot can be read like um, in the like here we have in the y-axis the beginning year, in the x-axis the ending year, and so each point shows one linear trend on picking every starting and ending date, and the diagonals correspond to the to same quantity of years of trend. For example, below this line, we can see the trends of less than uh, less than 5 years that really are super noisy. But if we go to from 5 to 20 years trend, we can see that periods are, we can already see the interdecadal variability with periods about around 20 years of increase and decrease of the temperature. And only above periods of 35 years, we can see a robust temperature trend. But in this case, it's a positive change of around 1.5 degrees that might be driven by climate change. However, these short periods are very important, as some studies have shown that that affects quite strongly both the cryosphere or the biosphere. For example, in this paper of Oliva and others, we can see that that this cooling period affected uh, the cryosphere in many regions of the Antarctic Peninsula. And in this paper of Sancho and others, they show how this cooling period also affects the growing of the lichens. Therefore, let's see a little bit the sources of interannual variability of the Antarctic Peninsula. This is shown before the last 10 years, but has been improved quite a lot, our knowledge on this source of variability in the last decade. So variability in the Antarctic Peninsula depends on the atmospheric and many atmospheric patterns, but especially the most important is the southern annular mode. That indicates the strength of the zonal winds. So when the sum is negative, the zonal winds are much lower, they slow down, and therefore they let to enter in very simplified intrusions from mid-latitude enter to the continent, which makes that does not warm too much the continent. Contrary, when it's positive, the circumpolar wind strengthens, creating a kind of wall that does not let the cold air, Antarctic air leave, while Antarctic Peninsula is still subject to the warm intrusions due to its position quite in the north. Therefore, Antarctic Peninsula is correlated positively with the sun, while East Antarctica is negatively correlated. However, as you can see, this picture is much more complicated that I show in the right, because also sun, it's not perfectly symmetric, even if considered as the symmetric pattern due to that is calculated with the difference of pressure between 65 and 45 degrees, I think. It's very asymmetric, and indeed it affects a lot the Antarctic Peninsula, and this is why the effect intrudes more to the south. The second mode of variability that most affect the Antarctic Peninsula is El Niño Southern Oscillation. The storms created in the West Pacific during El Niño or La Niña change creates a wave train in the upper atmosphere that translates towards the Antarctic Peninsula, modifying the temperatures there. Here it interacts as well with the Amundsen-Bellinghausen law, which is a climatological law that, uh, depending on its position and pressure dips, modulates the warm and moist intrusions from the Pacific. But it not only interacts with that, but also it interacts with the southern annular mode, making that the years of La Nina and positive sum being the warmer in the West Antarctic Peninsula, as shown in this study of Clem and others. So you can see that uh, all these interactions are very complex. This complexity adds as well with the sea ice, as shown, Carlos, before. Uh, it has been a big decrease, and sea ice also modulates, especially the cold temperatures. You can see this is plots are for Faraday-Bernatsky station. You can see a big decrease in cold days and a big increase in temperature that are driven by the big decrease in the sea ice around this station. But variability does not only affect the temperatures, but also wind. For example, there is this study that shows that some and ENSO patterns are more complex than just an increase or decrease of the winds over all the Antarctic Peninsula. And also it depends on the different months. And it also affects the precipitation, right? With some, it increased the precipitation in the West Antarctic Peninsula with increase of the sun, while it decreased in the East Antarctic Peninsula to the foreign winds. We could speak all the day long about these interactions, but since the time is limited, I can refer you to, for example, to this great review of Lee and others about the Antarctic teleconnections. So, seeing the importance and the magnitude of the variability in this region, one can ask, are then the temperatures observed caused by Antarctic climate change or due to the natural variability? If we see the time series of the Antarctic index, you can see that it has increased with the time. And we know that temperature in the Antarctic Peninsula increased with the sun. But Jones and others did a very interesting exercise in 2018. They calculated the temperature increase caused by the sun. As you can see, it's positive in Antarctic Peninsula and negative in the rest of Antarctica. They rest the trend caused by the background climate change, and you can see that it offset the increase in the Antarctic Peninsula and increase the non-statistical change in the rest of Antarctica, having a more homogeneous increase that it's on the magnitude of the world climate change. But the largest scale seems easy, but what about the extreme events? So when an extreme event occurs, people easily say that it was caused by climate change. But demonstrating that is climate change is not and not variability is not that easy. Indeed, not always possible. That's why about 10 years ago appeared the event attribution science. Of course, this attribution science started in Europe and America until 2022 did escape from Antarctica and was with the case of the February 2020 that first attribution study appeared in Antarctica and was followed by the case of February 2022. They were made by a method that is called analogs, but the most interesting thing is that these two very different events, uh, we observed the same amplification. We observed the climate change amplifies 25% in both cases, indicating that the method is robust. In the last in the last years, indeed, the atmospheric community is shifting the interest from the large scale to the shorter scale, and specifically to the extreme events. There is appearing different studies to understand the drivers of different phenomena, like atmospheric rivers, which is experimenting a great hype in the good sense, the blocking events, or the foehn events, also occupies many studies. And to ending, what about precipitation? Precipitation has been historically very difficult to study due to the unreliable observations like Gotchinder catchment, high spatial variability, and problems on understanding the microphysical of clouds and precipitation, which makes that reanalysis and models are very unreliable. Still, there is investigations on that showing, for example, that the most extreme precipitations in every time scale occurs at the Antarctic Peninsula. This table indeed also shows how these two different models, RAGMO and ERA5, provide for the same event very different precipitation, with RAGMO2 giving twice precipitation of ERA5. As I said before, it's very unreliable. Still, the quantities, the quantification of the precipitation. And we also know that precipitation is increasing, and this is because a warming atmosphere can hold more moisture, leading an increase of 77% of precipitation per degree of increase. Changes are not only in amounts, but also in the phase. Due to the increase of the temperature, the 0 degrees of term is shifting south, and with this is shifting south as well, rain and the difference between rain and snow phase. In the future, we expect that 0 degrees of term retreating around 25 kilometers per decade. We expect rainfall patterns move at around the same rate. Studies about rainfall, Bidon and others, conclude as well an increase of number of rain days by the end of the century, especially in the Antarctic Peninsula. So there is still many unknown questions about the weather and variability of Antarctic Peninsula. Here I show a big non-exhaustive list of research topics that need to study. However, I hope this short presentation might have helped to give a bit summary of the last decade of research in this general topic.